Cool. So the next presentation is from Javier from MPL in the UK. And he'll talk about metrological procedures in the context of satellite data interoperability. So please go ahead.
Okay. Hello to everybody. As he says, I'm Javier Gorroño, coming from the MPL, the National Physical Laboratory, which is a national metrological institute. Is the equivalent here in the US to NIST. And I want to talk about different metrological procedures which we think are helpful, especially in the radiometry for ARD products, what we talk about interoperability. So basically the definition, this is one of the many definitions we understand of ARD, is that the satellite data is prepared to the users to analyze without doing any pre-processing, typically at the level 2 or other levels. And the talk is that we've been considering different data format, different projections, but we are really interested in the potential radiometric and geometric phases, which require the uncertainty assessment and a traceable validation that actually provides consistent radiometric and geometric ARD products. I'm going to talk about 3 metrological concepts here in order to achieve a useful ARD from a radiometric point of view. I will use specific examples to define the metrological concepts. The first is the ESA project FRM4VEG, which are fiducial reference measurement of vegetation. So in this case, I will explain you what is this surface reflectance validation in order to generate a traceable reference, which is actually can be used as a benchmark for the ARD products. In this case, for example, level 2 surface reflectance. We'll go from the field campaign to diffuser calibration, the uncertainty in the reference itself that we provide, and the results. Then we'll work on how we can provide estimates on these ARD products, especially I will show a simple example of how commercial missions can do it. I will go into the example of the work I developed for the Sentinel II on the level 2 uncertainty I'm currently developing and some examples and so on. And finally, I will talk about an intercalibration traceability using the TRUTHS mission, which is an MPL-led mission, a new upcoming mission from ESA, in order to explain the consistency of commercial missions to reference missions like TRUTHS, or in this case, Sentinel II or others, or Landsat. So let's start by the FRM, what fiducial reference measurement means. In this case, we want to provide a fiducial reference measurement in the sense that we can demonstrate the traceability of the measurement, we can validate the data independently, and apart from that, we not only provide the measurement, the reference value of the surface, but we also provide uncertainty associated to the measurement. So this considers 3 components: the test measurement, the reference measurement, and the comparison procedure. In this case, what we are measuring is this value here, which is typically a HDRF if we assume that the satellite is actually quite directional, a hemispherical directional reflectance factor. So we base the first approach of these FRMs is the first phase. There will be a second phase, but in this first phase we went into Barracks, which is an area in Spain, and we follow a ground measurement of the area. We sample a 200 by 200 meter area with an ASD, and for each one of the samples, basically we had 6 individual measurements, 1 time the panel, for the surface, and again the panel. And as you can see here, so you've got the 10 measurements over the alfalfa field we sample here. And the satellite observation was on the 2nd of August last year, 1 year ago. The first thing I want to mention is that the sun zenith was at 25 degrees, so very important because we'll need to correct for the reflectance panel. And the viewing zenith angle is at 6 degrees, so in the forward scattering plane, which is not such a big issue, but obviously it introduces some level of uncertainty. I want to showcase what we try to deal with really precision, which is the diffuser reflectance, because it seems something obvious. You come to the field, you determine the diffuse illumination ratio, you derive the calibration coefficient, and you convolve the calibrated HDRF with the Sentinel II spectral bands. it seems a big effort, but actually it is important because it's not a tiny error, as I will show in the next slides. So we consider this is the direct case, and this is the real case you've got in the surface. You've got actually a diffuse component of the light, especially when you go into the blue areas. And these are the light conditions for calibration, which typically you calibrate at 45 degrees. But actually, the field conditions we find are the opposite. We need to assume reciprocity of the spectron, and the sun is actually at an illumination angle of 25 degrees. And why this is all important? Because we came with the original spectron calibration at 45 degrees, and we say, okay, we've got the curve, we just convolve, end of the story. But this, as I say, is not valid. And what we did is that we calibrated the diffuser at any illumination angle. And as you can see here, the diffuser calibration is massively changing from 1.6 to 0.97. So if you see here, this is the value of 25, and this is the value of 45. The difference is at the level of 3–4% if we do not correct for this. So actually, it's important that our reference, which is our benchmark for ARDs in this case, is taking into account these issues, this level of detail. And in order to calculate the diffuse component, we integrate it over all the potential illumination values. And actually, we use some microtopes in order to derive some aerosol and water vapor. And also very important is to actually derive some in situ data uncertainty. We do not only want to provide a benchmark measurement, but we want to provide an associated uncertainty with this measurement. So here you've got the equation of the derived surface reflectance, which is the irradiance multiplied by the calibration of the direct component and the diffuse component. And basically, it's just an example. It's going to grow quite a lot. We've got a leveling error. Then we introduce the row countings error, which is the instrument noise. We continue studying the direct calibration coefficient, which has an error. Obviously here, you've got the panel calibration error, the normalization to the sun angle, interpolation error. It grows. It becomes quite more complicated because the diffuse component must be integrated. This is the integral over some sort of trapezoidals. And you've got quite complicated equations here. And then you've got even more complicated situation here where you need to model. In this case, we use 6S to model the diffuse component and so on. In the end, we derive uncertainty estimates for these values and are actually based on this approach. So it's not an easy exercise, but for this case, for the fiducial reference measurement was the idea to provide a final value. So here you've got an example of the results. Basically, the Sentinel II against the reference measurements. In red, you can see the area where the Sentinel II requirement falls. And as you can see, in most of the cases, our results fall inside the Sentinel II requirements. So key messages of this part of the presentation is that a handheld spectrometer campaign provided us with a limited reference. We are considering that a typical ASD is a problematic thing if we want to go to a very fine level of detail, basically because the ASD has a broad viewing optics at the 8 level, at the 8 degrees field of view, lacks the pointing ability, and the collection time is also quite limited. So we are considering in the second phase of these FRM projects to actually go into a UAV-based collection, validation, that can actually replicate the angular sampling of Sentinel II or other missions, in this case Landsat 8 or whatever. The other thing is that I've shown you the importance of the diffuser panel calibration. It's very important that we actually have the spectral diffuse direct ratio and that we introduce the angular characterization of the reference panel. Without that, it's not an issue of 0.5%, it's an issue of 4% or more. So it's quite important. And any data comparison basically requires an uncertainty estimate for both the reference and the target. In this case, I've been showing you that in order to make the comparison, I have provided an uncertainty value of Sentinel II and an uncertainty value of the ASD collection. I've shown you how I derive the ASD uncertainty, and now in the next slides I will show you how I derive a preliminary Sentinel II uncertainty value. But basically we want to compare two values. If we don't have the uncertainty, it's a bit limited, the comparison. So basically the idea is that a fiducial reference is essential to determine the suitability of the data inputs for this ARD. So if we have, especially coming from ISA, these inputs that become the benchmark that you can actually compare the different inputs of the ARD products, like in this case Sentinel II and Landsat 8, and actually they are traceable to the same, they are comparable to the same reference benchmark on the ground. Now I move into the uncertainty estimates. As I said, I provided some estimate for the Sentinel II uncertainty of the level 2 product. I don't know if some of you are aware, but there is something called the radiometric uncertainty tool that we developed. Basically are operational uncertainty estimates of the Sentinel II, which provide level 1C uncertainty so far for the specific scene, pixel, processing, and uncertainty contribution. It's a very simplified approach that you can study also the correlation between the different pixels. It's an operational tool. It's not as part of the downloadable product that you can find, for example, in Copernicus Data Hub or in other sources, because basically it's quite a lot of data. It's built as a plugin that you can build, or you can use it as a, you can download and use it as part of the Snap desktop, and you can also use it from the batch mode. The problem is that when we come to ARD and data interoperability, we basically require not only uncertainty estimates of level 1, but we require uncertainty estimates of level 2 or further, and this comes big questions because I know I developed the level 1 uncertainty, but I know that many users do not really introduce as part of their pipelines because they basically do not know how to propagate from level 1 to level 2, or it requires a lot of effort. So basically I made a preliminary effort in trying to determine for this specific Barracks campaign the level 2 uncertainty. I went into the hard work, which is I got the level 1C uncertainty from the RUT, from the tool, and I modified each one of the level 1C product of the JPEG 2000 image using a Glamour package, and I propagate hundreds of times to level 2A using Send2Core. This is the hard way. It takes a lot of time, so you can think that it takes every iteration around 30 minutes. So basically you've got here an example of, illustrative example of how the process worked. And what I developed is a set of images of surface reflectance dispersion as a result of the propagated uncertainty of level 1. So you've got here an example of the band 1, I think, the band 2, the band 8, and the band 12. And you can see here that for each one of the pixels, you've got variations depending on whether you are in alfalfa, you are different, this is soil areas, and the uncertainty levels are completely different. I thought it was enough. I had the values I could ingest into the validation campaign, but then I took a look into a bit of detail, and it was not as simple as I thought, because there are many considerations. The first one of the most important, is that Send2Core and many other atmospheric corrections introduce an aerosol optical thickness retrieval. So in this case, the dense vegetation retrieval failed for a part of the distribution. The original product is correct, the dense vegetation, but when you get the dispersion of the values, for some part of the Gaussian distribution, the values of the dense vegetation of the aerosol optical thickness fails, and this is due to some thresholding, internal thresholding of the algorithm. And then the other thing is the importance of the pixel correlation. In this case, I want to show you the difference of the uncertainty when you consider a spectral correlation between the bands, or when you do not consider a spectral correlation between the bands. So it's completely different result. I mean, you need to consider the balance of, for example, let's say the diffuser calibration. You can assume that there is some certain level of spectral correlation in the uncertainty, but the instrument noise is not correlated. You can assume that the spectral correlation, the correlation between bands is zero in this case. So it's quite a challenging issue, as I said. And in this example here, I show you the result of the different iterations of the aerosol optical thickness. As you can see here, you get a typical dispersion of the aerosol optical thickness as a consequence of the level 1 uncertainty. And here, you've got the failure of the dark dense vegetation, which is the 40 kilometer visibility that is actually not updated. Okay, so for example, what happens if we continue with this propagation to further levels? You've got NDVI, for example, so you've got actually two different modes of NDVI. And actually, sometimes what it can happen is that this uncertainty is translated in some sort of temporal noise, where you think that actually something is happening in the site or in the instrument, but actually, for example, it can be simple that is changing a thresholding in the Sen2 core, you know. So it can be that kind of situation where you think that temporal noise is not really anything in the instrument, but a simple thresholding. Okay, I went into the most difficult thing, and then I come into, let's go into a simple case where we try to showcase something very simple. So what I did is that I got the level 1C uncertainty analytical propagation for 6SV, very typical case, using a Lambertian, and the only thing I need to do is to get the derivative with respect to the top of atmosphere reflectance. So I calculated the values, and especially, and very important this, I validated against a Monte Carlo. So I calculated analytically using this approach, and I validated the results against the Monte Carlo approach. So it's an important message that when you've got an uncertainty assessment, you try always to validate. For example, in this case, what we try to do is to use this analytical approach and validate against a Monte Carlo in order to verify that they match. You are getting actually the same approach. And what I did is that I introduced the aerosol optical thickness and water vapor requirements of Sentinel II in order to get a dispersion, and another allocation which introduces other issues like the relative transfer code accuracy, lookup table interpolation, adjacency, and so on. So the message from this is that providing optimum uncertainty estimates at the level 2 is going to be very challenging. It's not a straightforward thing, but we don't need at this point to provide the best uncertainty estimate. We can start with something like here I've been showing you, and on the background we can go doing very complicated issues, you know. Okay, so basically the outlook for these FRM, fiducial reference measurements, is that ESA is continuing funding this initiative, and has been funding for land, ocean, and atmosphere, different products. There are products from ocean color, temperature, vegetation, and so on. Is an initiative which is internationally coordinated by CEOs. There's a second phase of the FRM for BEDGE, where we will try to actually cooperate with Asia, Australia, and so on, and develop the super sites and try to bring this into a new upgraded results. And the idea is that the commercial missions should also use these FRM sites in order to benchmark the products. And the interesting thing is that, as I said before, a data comparison requires uncertainty estimates of both the reference and the target. So when you use the FRM measurements, you always need to have in your reference product some sort of level of uncertainty in order to understand the matching. You don't need to have the best uncertainty, but you can start with something very simple that actually is useful. Okay, the last thing, which I think I'm taking too much time, is I want to mention quickly about a new traceable intercalibration, which is based on the TRUTH mission. This TRUTH mission is an ESA Earthwatch mission, which is upcoming, provides continuously calibrated hyperspectral solar and lunar irradiance and top of atmosphere Earth reflectance radiance, as well as surface reflectance. The payload design was driven by the climate applications, basically at the level of 0.3% uncertainty, which is very, very, very low. And importantly, the mission orbit allows optimal sampling for different matchups of cross-calibration because it's asynchronous and is precessing orbit, so that means it's never repeated in the same place. The main features is a 5 to 8 year mission with 150 kilos and so on. It's got a hyperspectral imaging covering the V-near and SWIR. It's got an on-orbit and onboard SI traceable calibration, which aims at go at the 0.3% spectral radiance. This is thanks to the incorporation of a cryogenic radiometer, which is the standard of optical power. And as I said before, it's got a precessing orbit, which is going to be very useful to have different viewings and temporal acquisitions of the different areas of the Earth. So there are three main activities we are looking for developing a traceable intercalibration using truths that can be useful for the community. The first activity is the intercalibration orbit matchup, so define the events based on the latitude and longitude position, time span, and angular configuration. The second is the intercalibration performance assessment, which is identifying the best scenarios with an end-to-end sources of error at a global scale. And then finally, we've got an intercalibration product where we want to establish some gain curve efficient for the target sensor. We want to describe this in more detail. I think I'm going quite late, sorry. Sorry. And so we've got the spectral errors, we've got the spatial errors. We are trying to go into detail into each one of them. So we've got also the viewing errors, the polarization errors, and some sort of temporal error. These 5 sources of errors are very important. We've been looking at the detail at each one of them, as well as in conjunction with the Claro mission, which is the sister mission developed by NASA. But basically, the end-to-end performance analysis we want to look forward is we have studied each one of the individual errors, but we want to understand the global effect in an intercalibration coefficient. So we will need to understand the end-to-end bias, the uncertainty, and the correlation. So many missions, like here, base the radiometric calibration on an intercalibration. But we need to attach a reliable estimate. We need to study different intercalibration scenarios based on the uncertainty estimate, and we need to study the major effects on the uncertainty budget to actually define where to tackle the corrections. So we are considering a global scenario for truths where we have a matchup identification, a top of atmosphere modeling at a global coverage, and a final uncertainty calculation of the biases. That's all. A bit late, sorry. Thanks.
So if we can leave the questions for the end again. Next up, we have Beau from Esri about data management and access for global temporal ARD.
Thank you. Okay. Thank you. Good afternoon, everyone. I'm Beau Legeer from Esri, and I'm going to talk about data management and access for global temporal ARD using a data format, data structure that exists within the Esri software. So as an introduction, I will lay out something that everybody here knows, just set the background, basically that we are transitioning. I hope we have already transitioned, but the transition that's been going on in the last couple of years has really been in the analysis space from scene-based and project-based to really dealing with seamless time series data that allow us to do very large-scale analytics. And that's going to be the basis of what I'm going to talk about in this presentation. Because I'm going to deep dive into how do we achieve this goal. And we've heard so far the last 2 days several methods that other presenters have laid out, but I'm going to talk about one that allows easier access to data, easier use of the data, supports big data analytics and cloud-based platforms. Doesn't really focus you on one cloud-based platform. It can be any cloud-based platform. And empowers tailored web applications that really improve the usability of the data for your end users. So let's reflect a little bit on the past. And I like talking about this because 30 years ago, this was my life. I actually lived through this, what I call the dark ages, or the middle of the dark ages of data exploitation and analysis. And that was that we were completely scene-based, and we were not only that, we had to go through great cost and great time and great skill to actually get a single scene of data. The workflow that I went through almost 30 years ago was that I sat at my terminal at the NASA Goddard Space Flight Center, typed in some job control language on the IBM mainframe, which sent a job to get a tape mounted that had a Landsat scene on it. A couple days later, the tape got mounted. I got back a file unit to put into my Fortran 77 code, where I dealt with either one line of data, one spectra, depending on how the data was laid out, rinse and repeat over and over again. Those were the dark ages. Thank you for the cloud and for the internet and for evolution, because we can, you know, we got better. I mean, this is now, we're moving into the late 90s. That was the early 90s, late 80s, early 90s. And in the late 90s, early 2000s, we had the internet. We were still downloading single scenes. But then the USGS, probably some of you in this room, did something incredible with the seamless server. I remember going to Sioux Falls in 2001 or 2002 and seeing a Java applet-based seamless Mosaic. I thought it was the greatest thing ever. Because I saw the continental United States in Landsat all at once. You could click on the scenes and they would flip back and forth, and I could create a cloudless scene seamless. It was amazing. Now, the great thing, of course, was 2008, 2009, when Landsat was freed, and we heard about that yesterday. And then that really coincided with the cloud. And in 2010, Esri started to provide access to web services of certain flavors of Landsat data. This put out worldwide multispectral, multitemporal image services, as we call them, from Landsat. In 2012, we published this from a private cloud, and in 2010, we transitioned to the AWS Open Data Set. And the result was that all the Landsat data is available online through a web service. And this web service, through its REST API, through other API calls, gives you access, either catalog access, visualization, or just straight data access to the spatial components, spectral or temporal, of this service. Now, what I'm here to really talk about is how did we do that? How is it done? What's the method that empowers this global temporal data set? And the method is a Mosaic Data Set. So a Mosaic Data Set is a data structure that exists within the Esri software. And what it does is it allows you to store data, and you don't have to pre-process the data, because it stores references to the data and the metadata. And I'll go into gory details in a couple slides. But what it empowers is on-the-fly processing of the data, either radiometric processing, geometric tiling, all together. But the most important thing is the data stays at rest, either on your data store or in the cloud. And it is processed on the fly. You can also create and share analytic tasks that work on that data. These can be complete analysis workflows. You can share Jupyter notebooks that have direct access to the contents of this data. You can access this with Python scripts or share them either via Jupyter notebooks or via other formats. And you can also create custom geoprocessing services. So what does a Mosaic data set do? It manages imagery, and it manages the imagery on the left side of the display, primarily orthos, elevation, multi-dimensional data sets. It also manages LiDAR, and it does this from satellite, aerial, and unmanned platforms. So some of the characteristics is that it really is an optimal model for image management. It's very scalable. It can handle a single scene, a couple scenes, or it can handle Landsat, millions and millions of scenes. It is defined within the Esri geodatabase format, either a file geodatabase or an enterprise geodatabase. It references the sources. It doesn't duplicate or store them. It's very important for these large cloud stores. It just simply points to the data where it lives and accesses it as it's needed. But it does maintain the metadata about its sources. And it also defines the processing that's applied to either the individual components or the mosaic that it maintains on the whole. When it does do mosaicing, it defines mosaicing rules so that you can customize how that mosaic is presented to the user and allows you a large level of control over that. And there are overviews that are embedded that you can create that allow for a kind of a seamless viewing at multiple scales. Now this data set can be accessed as a single image, and that is a mosaic then, or as a catalog. So you can use it and search it and find its individual components. Now, I'm going to focus a lot of this talk on Landsat, but the Mosaic data set supports multiple data types, and the cascading menus here that are screenshotted just basically show the majority of the data types that exist within our community. Satellite data sources, aerial data sources, science missions, commercial missions, they're all supported. If it's not supported, we can create something called a Python raster type, where we can write you can write your support for your custom data type or data source. So how is a Mosaic data set structured? It has a big group layer, and that group layer contains footprints and boundaries of not only each item, but also of the entire extent of the mosaic. It also stores the seam lines if you're doing your advanced blending for mosaicing. And it stores, or it allows you to present an image to the user after applying all the processing and mosaic rules that it stores. There's also properties, what we call key properties are stored, and you can query them of the Mosaic data set and the raster items within them. And you can take this Mosaic data set and add it to an Esri desktop product or Esri web product, and those products will expose the layer properties and allow you to manipulate things like the mosaic methods, do queries on them, and go through the data set through time. So here's the schema. When you start with the Mosaic data set, you start with the properties on the Mosaic data set. The Mosaic data set also contains a footprint table, one of these for each item or scene in the Mosaic data set, and that contains a bunch of required data and optional metadata. You can also, which displays the footprint. Also, there is a raster item which is stored within this footprint table, which defines the processing chain that is applied for that raster item. And this can be anything you want. You can build these on the fly. You can build these when you publish the Mosaic data set. You can also use these on client, or you can also define these when you have clients. So going through, we also have more tables in this schema that define the seam lines. If it's a stereo pair, we can handle that. Different levels of visualization are stored within there, logs and raster types for extending the Mosaic data set. So a key element to the Mosaic data set is not only the storage, but also the processing. A key element here is the Mosaic data set supports processing on the fly. It supports two types of processing: dynamic on-the-fly processing, and it also supports large-scale raster analytics. So first, let me talk about the dynamic processing, which occurs on the fly. The Mosaic data set defines how the images are processed when they're accessed. And these are cumulative functions that are put together and they are run, and then resampling is only done once on the data set. So you don't do a raster function, then resample, raster function, resample. It's just all the functions are done together, and resampling is only done once. Each item can have a raster function, or you can define raster functions for the entire data set. You can do both. And these processing chains can be defined when you publish the Mosaic data set, and they can go along with the Mosaic data set, or users of the Mosaic data set, clients, can define their own to apply to an existing Mosaic data set. The other type of processing is Raster Analytics. These are a kind of larger scale asynchronous processing tasks. Think of processing an entire region or state worth of data, or country. The Mosaic data set can be used as input to this. And to do this, you use a product we have called the ArcGIS Image Server, and you configure it for the role of Raster Analytics. And it scales, it modifies the data properly so that it does proper cloud parallel processing, and this is how this works. And it's really meant to quickly process massive imagery or raster data sets in a scalable environment. So on the cloud is ideal. It executes advanced, customized raster analysis, and you can share the results with other people in your department or publicly within your enterprise. Okay, so I want to take this time to also point out that within the context of a Mosaic data set, we also support multi-dimensional data sets, either file-based data sets such as NetCDF, HDF, and GRIB, but also Mosaic data sets that contain these data. We do this all through a multi-dimensional API, and also the CRF format, which Peter talked about yesterday, is really just an optimized multi-dimensional data set. Okay, so when we have multi-dimensional data sets, we can access just files, single variables within a file, but the multi-dimensional Mosaic data set will allow us to access multiple variables from one or multiple files. So we have very diverse and extensive multi-dimensional raster support. Now, how do you share these data sets and these collections? I mean, it's really important. How do you actually get it out to people? How do you share? And the key there is you disseminate this through the ArcGIS platform in various formats. One is an image service. An image service holds and can give you the true pixel values. It can also apply the processing chains and deliver those to you through that dynamic processing component. This is also the service that can support live data. You can connect your Mosaic data set to a live data source if you have that coming in. We also have this concept of a map service, and map service is used primarily for visualization. It's more static in nature. Now, both of these services can also be delivered through OGC capabilities. You can send, or you can support WMS, WCS, and other capabilities from your Mosaic data set. So you can publish it and serve it that way if your clients support that as their service or preferred service. So what have we done with this? I'm actually going to show this. I think I'm the first person to try a live demo because it works. It's live, and I'm going to show you Landsat. There we go. Okay.
Okay, I need to get out of the slides, I think. Okay, now it should be get this thing here.
There it is.
But it should look there. Yeah.
Okay.
Just like that.
Okay. After I do this demo, you can go to this URL. I mean, I trust AWS with my life, but don't mess up my demo. Okay, so what we have here is the Landsat Explorer. What's going on here is I have a JavaScript-powered app that is hitting an AWS-powered web page that is consuming an image service that is consuming that is pointing to the Landsat data stored on the open data portal of AWS. This data is sitting in that bucket. We're not doing anything to it, or we haven't done anything to it. We're accessing it as it stands. So what you're seeing here is this is not a natural color image. I'm already manipulating the data. I'm delivering a different band combination. But because it's a Mosaic Data Set, I can do things on the fly. So the first thing I could do is change the rendering method. And you see these are all supported. So these are on-the-fly processing capabilities that I've enabled in the Mosaic Data Set. So I'm asking for a natural color. So what it's done is it's got that data at this resolution in this viewport, and done this, done the rendering, and it happened just that quick. I don't know where my mouse is. No. Oh, there we go. So I'm just going to show you like two more things because I can't really see the mouse. Okay, so I can go through time, and one of the nice things is I have a time slider, but I can also view this as a drop-down. So what's happened here is the application has used the web service to query this viewport for all the Landsat data stored in the Mosaic data set on AWS. This is what it returns. So you see, not only is it, it's got all the data in the viewport, but it is very current. We harvest this data and update the Mosaic data set on a regular basis. So I can change the time. I can also do very quick and dirty analytics. So in this case, I'm going to pick a point, and it went and did a spectral profile and tried to match that to a known material on the Landsat data. The last thing I'm going to show you, and there are many other things I could do here, such as change detection. And the last thing I'm going to show you on the time component, and this is what really excites me, is, let me get rid of this, is that when I view data, when I click on the time component, and I just click a pixel, just any location, what it's doing is it's going through the service and it's picking 20 or 50, I think I have it set to 20 points through time, 20 different Landsat scenes. So think about that. I have accessed 20 Landsat scenes, that point, and brought the the value of that point throughout time. Okay, that's not possible without a cloud service that can access multi-temporal data, do processing on the fly. Think about that with the use case I started off with the tapes. I mean, that's like 20 or 30 requests to read 1 pixel, which is what this is doing, but it happens instantaneously. So with that, in the instance of time, I will conclude my presentation.
Great. Next up, we have Alan from Planet. He's going to talk about towards ARD for Planet satellite imagery and about the atmospheric correction process.
Okay, I'm Alan, and I'm a software engineer at Planet, and I work on the atmospheric correction code. I promise there's not going to be any radiative transfer calculations on the screen here. Mostly pictures, so it should be nice and relaxing. Okay, brief introduction. In the context of ARD, what I'm really talking about is accurate calibration of the satellites that is needed, trying to get consistent reflectances, ground reflectances. And ideally, for it to be super useful, have daily coverage and it being global. And this will give you, hopefully, reliable time series data to analyze. For Planet, it's a little bit challenging. We have a lot of satellites, but they're not all the same. We have 4 different flavors up here that are up in the sky right now. And even in some of these, such as the Dove, there are multiple variations of that one satellite type. And you can see that they're not, there's lots of differences between them. They all have the RGB and infrared bands, but they're different spectral responses, the different center wavelengths. And, there's other things that are different about them. And speaking of the spectral responses, they're very different. And you can see that they don't really match up particularly well. And we have the new Super Doves that will be coming up soon, and they'll be different also. There will be Sentinel II-like, and I believe there's going to be multiple flavors of that. So getting something that is consistent across all of this is pretty much what we've been talking about this whole conference right now. So what about other satellites? That's just Planet. There's other satellites out there, at least I've been told. So I have up here comparing our DeVars satellites that's been up since around the beginning of the year compared to Landsat and Sentinel. The spectral response is getting a little bit more similar. And not only that, but they have different correction algorithms. So we have our correction algorithm. Landsat has theirs, and Sentinel II has another one. So how do you make them comparable? One is, which we've already heard about, is HLS. So that's making Landsat and Sentinel data comparable. And part of that is doing the same atmospheric correction algorithm for both of them. And that's what I'm going to focus on in this talk. Except I'm going to talk about it in the context of planet imagery. So what do we do for atmospheric correction? We do something pretty basic. We don't do a whole lot with it. We take existing code, software, where we find it. In this case, we're using 6SV to generate our lookup tables. And we're using MODIS data to collect atmospheric data. So the inputs that are going to be needed to do the correction. We do that because, for several reasons, but one is that the planet scenes are pretty small, so if we're going to do something like DDV, it generally doesn't work well because we don't have enough variety in the scene to even find enough dark pixels to make it work. There are other reasons, but MODIS data is there, it's good, so no reason not to use it. Once we have that, we just do pixel by pixel correction. We do make a number of assumptions and approximations right now. We assume that all of the satellites with the same build have basically the same spectral response. That's a pretty good approximation. We assume Lambertian ground model. We're assuming that everything's at sea level. We only use the average of the AOD and water vapor nose zone over the scene. That's also turns out to be pretty good approximation because, again, the scenes are pretty small. We use what we think are reasonable fallbacks, but we call those out when they are used, so users have it in the metadata and they know when that's done. We don't do any corrections for adjacency or BRD FFX. And we interpolate only between tables only for certain values, in this case for reflectance, AOD, and the solar zenith angles. The other ones we use the closest table that has that value. This is just illustrating sort of a very cartoonish data flow in our processing. On the top is basically what happens with planet data. We get it to the ground stations, we ingest it and do either rectification and compositing and determining the cloud mask at that time. Convert the radiance, get top of atmospheric reflectance, and then we have something that feed into the atmospheric correction. But we also ingest other data, imagery, and that's ongoing, and we can insert that at various points in our processing. And in particular, we ingest Landsat 8 and Sentinel II data. So in the end, what I've tried to do with the atmospheric correction is make sure that it's generic. I mean, it has to be generic because we have so many different satellites, I can't do something that's specific to one. So what the focus is defining what the inputs are, and up here basically the small set of inputs that go into it. The lookup tables either can be static or we can dynamically generate them, so either one, but usually we're using the static tables. And what comes out of it is a single multi-band geotiff with metadata embedded in it. And like I said, this doesn't care about where the input data is coming from. And what's the result? This is just sort of a picture book of example surface reflectance that's been generated through this process for each of our different satellites. The Dove is part of the strip, and it's all gone through the same code, and the code didn't care which one was going in. It's been validated using RadCalNet. And what's shown up here is data that was collected over a pretty extended period of time from 2017 through the beginning of, well, second quarter of 2019. And this shows you the overall accuracy and precision. And you can see there's quite a bit of scatter in this data. It's not ideal. So it's good to ask a question about, where is that coming from? And this shows at least part of the reason why there is some uncertainty there. On the left is the top of atmosphere, which comes from the same data set. You can see that there's already a significant amount of uncertainty in the top of atmosphere to begin with. And the input data for some of the sites, particularly Railroad Valley, like AOD, is very different from the MODIS data compared to what's measured on the ground. So, so even though there's a lot of scatter in the data, I think it's pretty good results, and it shows some consistency. What I'm now going to talk about a little bit, and throughout the rest of the talk, is look at comparisons between different satellites. And for us, I'll be referring to flocks. And the method I'm going to use is to look at an AOI and compare the reflectances from individual fields. So those fields are identified through the CLU database with common land units. And what that does is gives you roughly, generally, a homogeneous or semi-homogeneous area over which to average the reflectance values. And the one I'm using is in Sacramento Valley, and the time period I'm looking at is from January of this year to close to the end of July. I picked that time period because that will include the DeVars data in it. This just gives you an idea of what CLUs look like. So this is AOI, and it shows all the CLUs above 20 acres. If you went down lower than that, you'd get a whole lot more, probably into the, I don't remember how many you're in, 10,000, I don't know, too many. And so this is the kind of thing that will come out of it is, I'll show a lot of scatter plots. This is showing a comparison between DeVars for Dove over this AOI, and each data point here will represent one CLU at one particular crossover event between these two satellites. And you can see how they compare in each band with the dove on the x-axis and the dove on the y. Okay, so there's more than planets, and the question is, can this be applied to Landsat 8 and Sentinel? And the answer is sure, why not? We actively ingest some of that data, and they can be produced through the same pipeline because, again, the pipeline doesn't care what the data is coming from. It's all the same code. So what do we do with it? So first, I show the data that we actually have used in this comparison. And so it's the data for that AOI for that time period. And it's just a comparison of what the native surface reflectance from Landsat and Sentinel looks like when compared. Okay. And this is what it looks like if I use planet surface reflectance. So immediately you will see that there's a lot of benefit from using the same correction algorithm and code to process the data. In one case, it's two different correction algorithms. In the other case, they're the same thing. And that's all I've done between the two cases is a different correction. In this case, I'm comparing Landsat in both cases, but it's comparing the Landsat native versus planet surface reflectance. Landsat's on the X and planet's on the Y. And it's for each band. You can see how they differ for each band. There's pretty good agreement overall, and I haven't done enough analysis to know for sure where the differences are coming from entirely, but my guess would be is that because we're using the MODIS data, the AOD inputs are going to probably different because Landsat's, I believe, determining AOD from in-scene information. And so they're bound to be different, and that's probably where a lot of the difference comes in between these. And if we look at individual images, they look nice and pretty, and it's hard to tell, particularly on this screen, any differences between them. If you look close, you're going to notice the differences, but it looks actually pretty decent. Same thing for Sentinel II. Again, different correction algorithms that you have for Sentinel II. And so there's a little bit more of a difference here, different radiative transfer code used in the correction. Again, it looks actually pretty reasonable, and if you compare it to the others, it's not so bad. Again, looking at the images, look pretty similar. And now looking specifically at DeVars, and I'm looking at DeVars because the spectral response functions for it are more similar to Landsat than other DOVE data, so I'm just going to focus on that. We don't have a whole lot of data, but what we have looks pretty good. Nice and straight lines anyway. Oops, wrong way. And there's a little bit of scatter there, but again, if I look at top of atmosphere planet data versus the corrected reflectance, the scatter in the data is actually pretty similar, so it's mostly from uncertainty in the radiance. And this is the same thing, comparing it to Sentinel and DeVars. Again, quite a bit of scatter there, but it's also a lot of it coming from the radiance. So this is useful because it helps with looking at time series data. If you can get the corrections to be more similar, then you should be able to get more meaningful information out of time series. For this, I looked at data for an entire year, so it's for 2018. We won't have any DeVars data in it, but it'll cover the entire year. It's the same AOI, and it's using planet surface reflectance, so it's our correction for everything from this point. When looking at the time series, I wanted to sort of illustrate how it can be different at different times of the year. In this case, this is showing scatter plots where each color is representing a different month of the year, and the reds and pinks and colors are more in the winter, and the greens and blues are more in the summer. And you see that there's some definite differences as the year goes along in the errors. And I don't know all the reasons for that yet. I suspect, different times of the year, you think of sun elevation, and there's probably something in that. But also, I'm sure it has something to do with the changes in the ground cover as the year goes along and the effect on the correction. This is showing time series, various time series for the same time period, and these are for different CLUs, for different fields. And so there's different crops and different land cover throughout the year. And it's showing Rapid Eye, Landsat Sentinel II, and Planet Dove. So not DeVars, just Planet Dove. And overall, it's looking pretty decent. This is looking into one of the CLUs in a little bit more detail. Below, you can actually see what the field looks like. That's what in RGB. That's the field throughout the year, picked at different points. And you can see spikes in the planet data. I see that a lot. The cloud masking is not perfect, and so those scenes with clouds in them don't get filtered out entirely. And sometimes there's scenes with clouds in them and we get a little bit of stray light that has some effect. So you'll see some spikes in the data. And this is that same one looking at NDVI. Again, same changes overall in the data. It's not corrected for SBAP, and as I showed before, the spectral response for Dove is very different from the other satellites. So it's not surprising that there's going to be some overall difference there. And what about DeVars? This is just showing you what DeVars looks like for a little bit of data that we do have. This is, again, from that first data set from the beginning of the year and with some limited data. And it's looking pretty good. I think it's overall, especially at the peak there, the data is a little bit more consistent than it is for Dove, and which is what we would expect. And so, in summary, overall, I think going through this helped validate our approach to atmospheric correction, at least for now, for what we need and for the level of accuracy that we can expect. It definitely points to needed improvements. And I think it helps at least a little bit confirm that, going to spectral band response that is more similar to other satellites is going to help us out a lot. And because I'm a software engineer, I have a little bit of tips at the end, which I hope as you're developing your own software, you kind of think about, because there are a lot of advantages to producing these generic kinds of interfaces that doesn't care where the data is coming from, and makes it a lot easier to use. In fact, for doing this, the biggest part of the job was simply translating the metadata for Landsat and Sentinel and anything else to the input data. That was it. Nothing else really needed to be done except generate the lookup tables. And the plug for Planet at the end. Thank you.
Can Javier and Beau please come up as well? We can start the panel discussion. Cool. So the floor is open for any questions, if anyone wants to ask any. Sure.
Yeah, actually, so I have a question for each person. First, Javier, do you think, actually this one's actually kind of a question maybe for everybody, but do you think that there's a need in the future for an independent certification board for commercial satellites? Like this wouldn't be something that would be required. Like this would be like an ISO, let's say, like where there's an independent test done, and those uncertainties come out of that independent test of the data that then the companies would then use in marketing or whatever. Because right now it's really self-policed, right? Like it's up to the data provider to provide those uncertainty estimates, and they can use whatever data they want to create that.
So actually, you are talking basically about an audit in a way, which actually is the focus of the talk I will be giving tomorrow. It's a framework called EDAP, which is looking into that direction, where there is an external body which actually verifies the quality of the data through uncertainty assessments and so on. So it's actually the focus of the talk tomorrow. So I will be discussing that.
All right, so I can have more questions tomorrow about that. Beau, what's Esri's current take on incorporating or using STAC?
So we, more than likely, we will incorporate STAC. We're going to wait a little bit for it to stabilize. But once it stabilizes, we're going to put it in probably to the Mosaic Data Set.
Okay.
So we'll probably start by writing a custom Python raster type that accesses STAC items. That potentially extends to searching STAC, but that's really looking to you guys to make that, easier. But I would say you'll see it supported relatively soon.
Okay.
Yeah.
Cool. All right, and
Alan.
so all right, so now this is, I don't know, maybe this is part comment, part question, but so the AOD, you're using Modo 8 from Modus, which is notoriously filled with gaps daily, especially like over deserts, and there's other way. Traditionally, people would like gap fill these using like a running average from previous years, or looking at the months. I was surprised to see that you guys use a clear sky AOD as a default. So
Yeah.
why would that be?
Because it was easy. And
That's a
actually
great
the
answer.
original reason, and we just haven't changed it. And oddly enough, I'm surprised, but we haven't got any complaints about it either.
It's a major. It can make. That's the major driver, right, for the atmosphere.
And I did look at comparing it to doing this average, and I looked at averaging in various time scales of the Modus data, and what I was seeing is I wasn't getting good results out of it. It wasn't giving me any better results than if I just used clear sky.
Okay.
So I wasn't really motivated to
change it.
to do that, because it didn't seem like it was going to really help that much, if at all.
Right. Okay. Thank you all.
My first question is for Javier. So, your approach to uncertainty measurement is extremely thorough. But you mentioned that there are things that everybody could and should be doing to do at least some measure of uncertainty. And just sort of at sort of a top level, I was just wondering, what are some of the key things that you would like to see every satellite provider address, or like factors that they would use to make sure that their uncertainty calculations are valid?
That's a good question, because that was the intention of that slide, to bring all the complications and then say, okay, let's go into something easy. And actually, it was nice to see the talk later on from Alan, which actually they are using 6S. So for example, you can simply you can go into a complex Jacobian and so on and so on and so on, or you can start with a derivative of the 6S typical equation for Lambertian approach. And as I shown in the slide, and actually to derive the uncertainty propagation from the level 1 to the level 2. And then, for example, for MODIS, use a default aerosol optical thickness uncertainty in the MODIS products that you can derive if there is a formula of success maybe, and if you cannot, you can derive a lookup table of potential uncertainty values to combine with the uncertainty propagated. That could be a simple solution from level 1 to level 2. And at level 1, what I would simply use is something very simple, is to actually derive a noise estimate based on the radiance level, combined with some simple calibration coefficient uncertainty of the intercalibration process. So at level 1, these two things, noise of the instrument and intercalibration coefficient, and then from level 1 to level 2, actually the propagation and some simple estimates of aerosol, water vapor, and so on. I mean, it's not the best, but it's something, you know.
I also have a question for Alan. Yeah, you know, in your a lot of your plots, I noticed there was, you know, no direct mention of the like the measurements of the uncertainty levels, and I was just wondering, you know, is that something that you calculate, and if so, do you can you give sort of a sense of where those numbers are at, and also the scene that you selected, the place that you selected, I was just wondering, you know, you collect so much data over so many areas. Would you consider that a representative case or like a best case? Is it, you know, is that, does that, you know, where does that sit in your range of results?
Okay. The uncertainties, I mean, mostly what I have is just for the rad count net sites. So I haven't really looked at the numbers for, you know, other things like this, because I'm not sure how meaningful they are, because we need something to compare it to. As far as representative, I think it's representative as far as the kind of ground cover that most of our customers care about, in the sense that it's farmland mostly. It's maybe atypical in that it's in a nice, clear, convenient place where you don't have nearly as much cloud. If it was Midwest, there would be a whole lot less data to show, because half the time there would be a lot of clouds. So,
thank you.
Minsu.
Thank you. I have a question to Alan. I think your description of the method is extremely clear. It can't be any straightforward than that. But I had a little issue with the results. So first, my question is, you showed 4 scatter plots, blue, green, red, and near infrared. And the number was so small, tiny, so I couldn't even see the number. Maybe it was intended, but. So each axis, at the origin, it's all 0, or did you scale?
yes.
Okay.
Yes.
Then I have an issue.
Okay.
Because usually if the atmosphere correction is properly done, then you should be able to observe, let's say, the scattergram of the chunk of data. For first blue channel, it has to be much lower, because the numbers are very low at blue channel for the typical Earth surface pixels. And green has to be substantially pushed up a little bit, right? Not much, but there has to be definite differences. The location of on the one-to-one line.
Right.
And also, one thing that clearly bothers me is, by the way, the pixel area, you got a lot of water pixels.
I don't think they should include any water.
And you
pixels.
showed us a lot of example results, but consistently the NIL, the scatter plot, the data set, the dynamic range was very low. It has to be at least 20% or much higher.
Yeah,
Right.
the scales on the x-axis are different in each plot as well.
But you said it was 0, all 0.
Oh, it starts at 0, but the maximum is different. So and I apologize for the scales. I did the plots earlier
All right.
before I made my, and it didn't have.
Oh,
a
max
sense.
is not 1 then?
No,
I thought it's 0 to 1.
no, they're scaled independently so that they're spread
okay.
out as much as possible. And I
Yeah.
apologize for that.
Right, thank you.
Cool. I have one question for Javier. I guess one of the limitations of this kind of approach of a reference site is that you mentioned yourself is that you have to have lots of different sites to accommodate different terrain types and different parts of the dynamic range. How wide a range do you feel like you need to get an accurate picture?
Actually, you are referring to the fiducial reference
Yeah.
measurements.
Yeah.
No, basically, I agree that we cannot cover all the ranges, but we are looking for different vegetation areas, which are, it covers LAI, FAPAR, and so on. So one of the other requirements is surface reflectance. And for the surface reflectance, actually, we were discussing with the rest of our colleagues that they are looking at LAI validation, so they are looking for a forest area and so on, whereas in our case, we're looking for other more homogeneous areas and so on to actually validate. And that's where, when I started to talk about the drone systems, UAV, because that's when we can actually characterize different areas in very quick time. So that's our, in terms of surface reflectance, that's what we are looking for a UAV, which actually provides directional measurements, not like the ASD typical measurements, and very quick, different types of terrain.
That sounds interesting. Cool. Maybe one last question.
This is a question for Javier. I'm curious to know if you know of, or if there will be at any point any maybe like documentation or tutorials for how to propagate uncertainty data throughout Sentinel II processing levels.
Well, the tool itself has a tutorial, very simple, HTML, where it explains how to use it. We have actually published a paper about the level 1 uncertainty, how it works, and we published another one about how to combine different pixels and to understand the correlation in the spatial, temporal, and spectral domain. So right now I'm working in some paper in order to describe a simplified approach for level 2 uncertainty, and our idea is to continue there in that process, but slowly and finding all the issues and
These will be in the GitHub repository, or?
We are aiming to actually publish it in a peer review.
Okay, great. Let's thank the panel again. And we're having